So today I will be explaining an important paradigm because most of the time you used to work on first best parse, but sometimes you can have a base parser, let's call it a base parser, that produces k best instead of one best parse, and then you give it to another parser. So you have two parsers. But this we call it reranker. Because and it has nice properties. For example, if you write the probability of a parse, you will see that the denominator, for example, k from 1 to 50, getting the 50 best parses. The denominator is more tractable instead of an exponential number of parsers. So this is really interesting. And experiments have shown that it produces very good results. So that's why re-ranking is really important. Not only in parsing, in computational linguistics, but in machine learning in general. You can apply to different, for example, information extraction. You can apply to classical machine learning. So it has, so we have, for example, regression. A different world is classification, but a total different world is a re-ranking or ranking, let's say, ranking. And so that's the motivation. So I want to explain this article in 2005, but it is very similar to ideas of Michael Collins and or Charniak. These two guys were the source of inspiration for many articles on re-ranking parsers because they have shown us a different look at parsing and how re-ranking is useful in practice to have scalable algorithms. Two amazing scholars. And so why re-ranking? As I said, if you have watched my playlist for probabilistic context-free grammar, so the PCFG parser it just produces the n-best parse trees, and you give that to a feature extractor to create some parse description, and so this is your re-ranker. Your re-ranker, the second parse that I was talking about. And for example, this is the k-based, for example, you see two parsers. This is the second based parse. You can set k equal to 20 or 50 best parse. So you may ask, why k-best? Well, we postpone disambiguation, as Liang Huang in his slide has shown very beautifully, or propagate k-best least instead of one best. But if you read this article, a search-burst dynamic re-ranking model for dependency parsing, you will see how they outperform state-of-the-art models for dependency parsing by just re-ranking. But how do we generate k-best parsers? There are lots of articles, lots of methods to create these k-best parsers. Some of them use dynamic programming, but some of them don't use dynamic programming. So the re-ranker is this part that I said. I will explain it. We use the maximum entropy re-ranker. And re-ranker is simpler because the re-ranker only has to consider a relatively small number of parsers per sentence. So it is not necessary to use dynamic programming because we had problems with the denominator. It was exponential. We didn't know how to model it. But if it is just k from 1 to 20 or 50, then it is very fast. You can do it tractably. And there are two ways to recover the n-best parse using coarse to fine parsing. The obvious way and the clever way. And both of them use the dynamic programming to create n best parsers. So let's focus on this obvious way, or the clever way. The clever way is that the basic idea is to first find the best parse, and then find the second best parse, and then the third. And so you see that this was originally defined for hidden Markov models. And the obvious way is that rather than storing a single best parse of each edge, one stores n of them. That is when using dynamic programming. So rather than throwing away a candidate if it scores less than the best, one keeps it if it is one of the top n analysis for this edge discovered so far. So the obvious way, if you have seen my lectures on PCFG, the probability of constituent of type I spanning the words from J to K is equal to this. And the alpha is the outside probability, beta is the inside probability. And so you can very quickly identify the probability of a constituent of type I spanning the words from J to K. And so features for re-ranking, because just like any linear models, to model these features, you can have different categories. For example, they used over 1 million features for re-ranking parsers. And there are different categories. If you look at the article, you can focus on them and see how these categories are defined. Each have many features. There are many features that I skipped them. So the score of a parse can be defined just like any other linear model, just a weighted combination of those features, m features. For example, you have m features. And so the re-ranking, if we have trained that, then we know theta. After training, then we know theta, then we can evaluate the score of a parse. So given a string, the re-ranking parser's output on a string is the highest scoring parse in the n best parse. And we can estimate the feature weights. We have we have the loss and the regularizer. So if you have a correct parse, then it is not necessary that it is inside the n best parse. But if you're lucky, your correct parse is one of your, for example, 50 parses. Then one of them, if you're lucky, one of them is the correct parse, which is y star of your sentence or string. And so we are estimating the feature weights. So this is the standard maximum entropy conditional probability model. And this is the score. So it's just a softmax on the score. Because this y is short, it's just 50 or 20. And then the loss function L of D is just a negative likelihood conditional likelihood of the best parses. And we use the quadratic regularizer, this Gaussian or quadratic regularizer